I will put an announcement on Outline, okay, to give you some dates and times where you can come and ask any questions that you have, okay. But nevertheless, between now and the examination and the exam, if you have got any questions, you can email me, you can ask me to meet you, whatever, okay. So just get in touch. So what I'm going to do today is going through an example of a portrait frame. So let me share my screen. First of all, let me start recording, okay? So I'm going to start the recording now. Oh, someone is recording it, isn't it? That's fine. Right, okay, so let me share the screen with you. Okay, so so this is what we have. We have a portrait frame with some horizontal loading in the horizontal direction, okay? So what we're going to do is, today is analyze the frame by considering all the collapse mechanisms and then draw the bending moment diagram for the frame, okay? So just to refresh, as a refresher, the rules for determining the mechanisms are the total number of possible hinges, possible plastic hinges, M, the degree of redundancy, which is the number of unknown reactions -3, and the number of independent mechanisms being the difference of the two, M and N. And finally, N plus 1 will give us the number of plastic hinges that we need for complete collapse, okay? So, but remember, when you are analyzing a structure, you need to consider the combined mechanisms as well as the independent mechanisms, okay? And the following example is a good one where we shouldn't miss any of the independent mechanisms, okay? So this is the portrait frame that we have. So we have a rectangular portrait frame, which is not symmetrical. The geometry is not symmetrical and the loading is not symmetrical, okay? So the columns are 3 meters for AC and 6 meters high for GE. The beam is 8 meters long. And then we have horizontal loads on the columns. So we have lambda times 15 for the horizontal load on AC and lambda times 15 for the horizontal load on column EG, and then lambda times 20 for the column, for the beam, sorry, CE. Given, the lambdas are given to us. In the horizontal direction, the lambda is 1.4, and in the vertical direction, lambda is given as 1.7. So therefore, you can work out the actual critical loads by multiplying 15 and 15 by 1.4, and multiplying the vertical load, the 20, by 1.7. That will give you the critical load. Okay? I think it gives 34 for the vertical load, and I think 21 times 15 times 1.4, okay, for the horizontal loading. Okay, so this is the problem. And what we need to do, by considering all the collapse, all the possible collapse mechanisms, we need to determine the plastic moment MP corresponding to the critical mechanism, and then draw the bending moment diagram for that mechanism, okay? For this particular problem, we assume that MP is the same for the columns and the beam, all right? In other words, the beam and the columns have got the same cross-sectional area, okay? But in practice, they probably would not be the same, but for the sake of simplicity, we assume that MP is the same throughout. So using the rules, so in this case, we have we have 5 possible hinges, A, C, E, we have 5 possible hinges at B, at C, at D, at E, and at F. There are no hinges at A and G because we have pin supports, okay? In this case, A and G are not fixed, so there are no hinges forming at A and G, okay? So we have hinges only at B, C, D, E, and F. Then, for the degree of redundancy, we have 2 unknowns, 2 reactions at A, 2 reactions at G, so a total of 4, minus 3 equations of equilibrium. So we have 1 degree of redundancy in this case, okay? So the degree of redundancy is 1 in this case, right? And the difference of m minus little n, 5 minus 1 equals to 4. So we have 4 independent mechanisms. Okay, we have 4 independent mechanisms, which are obvious. We have the beam mechanism here for CA. We have the beam mechanism for CE. We have the beam mechanism for EG. Then we have the sway of the frame. So these are the 4 independent mechanisms. N plus 1, in this case, N is 1, so 1 plus 1 is 2. We only need 2 hinges for complete collapse, okay? So although we have 5 possible plastic hinges, we actually only require 2 for total collapse, as we will see when we start dealing with the mechanisms, okay? So we have 4 independent mechanisms, but remember, we need to consider any combinations, any combined mechanisms of the individual mechanisms, okay? If you have any questions, please just say so, okay? So beam mechanism 1. So this is beam CE. This is the beam, okay? So we have a load of 34 kilonewtons. And then we have hinges forming at these 2 supports here, not supports, sorry, at the corners here, and then in the middle, okay, because the load is applied in the middle, okay? This is beam CE, okay? And the displacement where the load is applied is 4 theta, because this span here is 4 and the span here is 4, so we have symmetry, okay? The total span is 8 meters, so we have symmetry, and therefore the length from this corner, from the column to the mid of the beam is 4 meters, so therefore the displacement here is 4 times theta, okay? 4 here times theta. Then the moments, we have MP at C, MP at D, this is D here, and MP at E. So therefore, the work will be, external work will be 34 times 4 theta, this is the external work, equals MP theta, MP theta, MP theta, and MP theta. So we have 4 MP theta for the external, for the internal work. The 4 and 4 here will cancel, and the theta with theta will cancel, and therefore MP is equal to 35 kilonewton meters. Okay, so MP for this mechanism is 34 kilonewton meters. Is that clear, everyone? Okay. Then the next mechanism will be for beam AB. We call it a beam mechanism, but we are talking here about the column. Okay, so it's vertical column AB. Okay, but it is effectively a beam type mechanism. Okay, so this is the
Sure.
Yes.
Isn't it beam AC?
Yes, probably, because AC is the column, isn't it? Yes, it is AC. Okay. So we have got. Let me rectify it. So we have got BC, okay, and it's similar to the previous one, to CE, okay, it's very similar. The only thing is that we have got it in the vertical direction, and also what you need to remember here is that because the support A is not fixed, is pinned, so therefore there is no hinge forming at A here. This is A, there is no hinge there. So we only have a plastic hinge at B and at C, okay? So therefore we have 21, that's the load, times the displacement 1.5 theta, because the distance from A to B is 1.5 meters, and from B to C is 1.5 meters, okay? It's symmetrical, and the load is at midspan, okay? So we have 21 times 1.5 theta equals MP theta and MP theta here, plus MP theta at C, so that's 3 MP theta. Theta and theta will cancel, and then we have 21 times 1.5 divided by 3. 21 divided by 3 is 7. 7 times 1.5 is 10.5 kilonewton meters. Okay, and that's the answer. That's MP for beam AC. Okay. The next one is EG. And that's the column on the right. Okay, so we have got a similar situation as beam AC. The only difference is that the span is different here. We have 6 meters. The total here is 6 meters instead of 3 meters. Okay, so therefore, otherwise we have a hinge at E, a hinge at F, and there is no hinge at G. There is no hinge at G. And the load is 21 kilonewtons, okay? So the external work will be 21 times the displacement here, 3 theta, equals to MP theta 3 times, MP theta, and MP theta, okay? So therefore the 3 with the 3 and the theta will cancel, and therefore MP in this case is 21 kilonewton meters. Okay. Any questions? Please just unmute yourself and ask, please. Okay, thank you. Next is, what is next? The sway. So now we have got the sway of the frame as a whole, and this is the frame with the sway mechanism in brown or orange color. So again, we have got there are no hinges at A and G. Okay, at the supports there are no hinges, right? And this is how the frame is going to sway under the loading, under the horizontal loading. So we have 21 kilonewtons on the left column at midspan, and we have 21 kilonewtons on the right column again at midspan. The displacement, there are 2 hinges. There is a hinge at the left corner, and there is a hinge here at the right corner. Right? And therefore we have MP and MP at both hinges. Now the frame will undergo a simple horizontal movement, okay? So there is a simple horizontal movement. The frame pushed by the horizontal loading, the horizontal loading will undergo simple horizontal movement. So therefore, the displacement at this end, at the top of the column here, will be equal to the displacement at the top of the column on the right. So therefore, for compatibility, we have got 3 theta is equal to 6 theta. Okay, theta is the angle of rotation of the left column, and beta is the angle of rotation of the right column. So we have 3 theta equals 6 beta. So therefore, theta is equal to 2 theta. Okay, right. So that gives us the relationship between the angles of rotation of the 2 columns. Now we can write the external work equal to the internal work. So the external work, we have 21 times the displacement. Be careful, it's the displacement where the load is applied. So it will be the displacement here, okay? So it's half of 3 theta. So therefore we have 21 times 1.5 theta, okay? So similarly here, it's 21 kilonewtons times the displacement where the load is applied, which is half of 6 theta, so it's 3 theta here. So the displacement here is 3 theta. So we have 21 theta equals, we have MP theta at this joint plus MP beta at this joint here. Okay, and what I'm going to do, we can substitute the theta everywhere by beta, or you can substitute beta everywhere by theta, whichever one you wanted. You can substitute theta by 2 beta, or you can substitute beta by half theta, and you get exactly the same answer here when you substitute. I mean, what I've done here, I've substituted theta by 2 beta. So that becomes 3 beta here. That becomes, and then we have 3 beta, 2 beta, and beta. Okay? So therefore, the betas will cancel. 6 and 3 we cancel by 2. Okay? So, and therefore, we have 21 times 3, which is 42 kilonewtons. Okay? So we have MP is 42 kilonewton meters. Is that clear? Everyone, please?
Yes, sir.
Okay, so moving on. So this is the sway mechanism. Now we are going to start considering the combinations. Okay, these are the independent mechanisms that we have identified. We said 4 independent mechanisms, and we've got the 4 covered here. You can see, please notice that we have only got 2 hinges for these mechanisms, which is what we said at the start, that we only need 2 hinges for total collapse, and we have only got 2 hinges and 2 hinges here. So the next mechanisms will be to consider the combination of the individual mechanisms. All right. Now, the first combination is to consider the beam CE with the sway. In other words, we have got the vertical loading here. That's the beam mechanism, and we have got the sway mechanism, which we have just covered. Okay, so when you put the two together, when you combine the beam, this beam here, this beam mechanism with the sway mechanism, you get this combined mechanism. Remember what we said before: when you combine the beam and the sway mechanism, this beam and the sway mechanism, the hinge at this corner here will cancel. Why? Because this column and this beam, this part of the beam here, rotate in the same direction. Okay, they both rotating. In this case, they are rotating clockwise. Okay, so this column and this beam are rotating in the same direction, clockwise. So therefore, this joint here will remain rigid. Okay, and there is no hinge rotating, which is not the case on the left, on the right here. On the right side, the column and the beam are rotating in opposite directions, so they come closer. So therefore, there is a hinge forming at this corner here. All right. So therefore, we have 2 hinges: a hinge at mid-span here, and the hinge on the right corner between the beam on the column here. Okay, and this is the mechanism. So we have got the vertical loading, 34, and we have the horizontal loading to consider as well. Okay, the displacement for compatibility, we have the same displacement, 3 theta and 6 theta and 6 beta. They are equal, so we can find the relationship between the angle there and there. Okay, so we have 3 theta, which is the displacement here, is equal to 6 theta, the displacement there, and therefore theta will be equal to 2 beta, right? So the next thing is to write the external work equal to the internal work. Okay, is the mechanism clear to everyone, please? Is it clear? Okay, so yes. External work. So we have got 21. Okay, this is the load here. This 21 times the displacement, which is this displacement, which is half of 3 theta. So that's 1.5 plus 21 here times 3 beta. Okay, here plus the vertical load, the 34, times the displacement, and this displacement is 4 times theta, okay, 4 times theta, right? Okay, 4 times theta, because the span, the total span of the beam is 8 meters, and half the span is 4 meters, so the displacement here is 4 times theta, okay, equals mp theta, and the mp theta, I think have I made a mistake here? I think, no, this is here, sorry. This should be theta, isn't it, here? Yeah, so we have mp theta, mp theta, mp theta, mp theta, that's 3 mp theta, and mp beta there, okay? All right, now we can substitute everywhere, we can substitute theta by beta if you want. Okay, so that becomes 1.5 theta becomes 3 beta, plus 21 3 beta, plus 4 theta will become 8 beta here, okay? Theta is 2 beta and mp beta, okay? Simplifying, we'll have 398 beta equals 7, okay? 3 times 2, 6 plus 1, 7 mp beta. And if you divide 398 by 7, you get 56.86 kilonewton meter. And this is the plastic moment, the moment of resistance for this combined mechanism. Any questions on this mechanism, please? Anything at all? Okay, clear. Okay, now we, what's the next thing? The next thing is we need to consider a combination this time. Remember, we have got a beam mechanism on this side and the beam mechanism on this side here. Okay, so the next thing is to consider combining this mechanism here with the beam mechanism for column EG. Okay, now you can ask me, why don't we consider the combined, combining with the mechanism of this beam? Can you tell me why it will be a waste of time to do it? Why will we consider only the combination, the combined mechanism of this with the column EG and not this column here?
Because it should give us the half result.
Sorry, because?
It should give us the half results of the other one, I think.
I haven't tried it. Now I can give you a good reason for the future to remember, okay? When you're combining mechanisms, don't consider combinations that will give you more hinges, because you will get you get a smaller value for moment, okay? Because look, if you take this, if you combine this with the this beam mechanism here, this hinge will not disappear. You will have a hinge here. Okay, you will have a hinge there, because if you combine it, you get a hinge there, a hinge there, a hinge there. So you have 3 hinges, more than actually you need, more than that what you need. Okay, more than that what you need for total collapse. So therefore, this will be a complete waste of time to consider combining this mechanism here with the AC, with this one. So therefore, the combination we consider is this one here. Why? Because if we combine this mechanism now with this beam mechanism for EG, what we get, this hinge will be eliminated, okay? Will be eliminated, but we'll have a hinge forming at this point here, F, okay? So let me show you. We are combining 5 and 6, and this is what you get. This is the combined mechanism for the, beam AC, the sway, and the and this beam here. So effectively what we have sway plus beam mechanism plus another beam mechanism. And you can see what happened is that because now this beam and this part of the column rotating in the same direction anti-clockwise, so this hinge will cancel, and now we have a hinge at the 34 kilonewton here, and then we have a hinge at the 21 kilonewton on the right. And this is the combined mechanism of effectively three independent mechanisms. All right, and let me explain now the geometry a little bit, okay, because it's a bit tricky, a bit complicated, not very complicated, but I just need to explain it, okay? So we start from the left, we have hinge, we have angle theta at this column here, all right? So therefore we have theta there and theta here, okay? Therefore, for symmetry, we have theta and theta there, okay? We have, because the beam is symmetrical, so we have theta and theta, all right? Then, because the hinge here, because this there is no hinge forming at this corner and it remains rigid, therefore the angle theta here is the same as the angle theta there with the vertical. And you see the vertical line here, we have theta and theta, okay? We have theta and theta. Now, from the sway mechanism, this is beta, okay? We have beta here and beta there, okay? And this is the vertical line, and this is the sway line, okay? This is where the sway we have, so we have beta and beta. So the angle, the total angle here is theta plus beta. The total here is angle theta plus beta. Now, if you look at this beam mechanism here, okay, can you see that? This beam mechanism here, we have symmetry, so the angle there, this angle is theta plus beta equal to here, this one here, theta plus beta, we have theta plus beta. So the total angle at, for this column, the total angle for this part of the column here with the vertical line is 2 beta plus theta, 2 beta plus theta, okay? And therefore, if you come here to the beam, if you draw horizontal, the horizontal line or vertical line, if you want for the column here, we have theta on this side, which is theta equal to theta, and then we have 2 beta plus theta on this side. Is that okay or not? Are the angles clear, please?
Yes, sir.
Okay. The other way you can, there is a different way you can obtain this angle is by using the principle of superposition, okay? All right, so we have, so therefore, now, once we've got the angles, the rest is easy because now you can write the external work equal to the internal work. Okay, let's do it. So we have 21 times the displacement here, 1.5 theta, plus this here, the 21 here times the displacement, which is 3, that's the length, 3 times 2 beta plus theta, okay? So this displacement here, okay? Plus 34 times 4 theta, okay? This is the displacement here, 4 theta, equals MP theta plus MP theta plus MP theta, that's 3 MP theta, and then MP times 2 beta plus theta, MP times 2 beta plus theta, which is the internal work for this part of the column, right? Now I'm going to substitute theta by 2 beta everywhere here, okay? So we have, that becomes 3 beta, that becomes 3, theta is 2 beta, so you have 2 beta plus 2 beta, that's 4 beta, 4 times 3, 12 beta, and then 2 beta times 4 is 8 beta, that's 2 beta, that's 2 beta plus 2 beta, 4 beta, And therefore, you can simplify now here. That becomes 3 times 2, 6, plus 4, 10. Okay, and this here, when you multiply 21 times 3 plus 21 times 12 times plus 34 times 8, it gives you 587 beta. Simplify beta and beta. 587 divided by 7 gives, not 7, it's actually 10 here, sorry. Okay, the answer is correct, okay. Okay, sorry. So we have got, so the moment MP, the moment MP for this combined mechanism is 58.7 kilonewton. And there are no more independent mechanisms to consider. As I said, this one here will be completely irrelevant, okay? So in summary, we have beam CE. Okay, is that that's AC, isn't it? Okay. We have beam CE mechanism gave 35 kilonewton meters. Beam AC gave 10.5. Beam EG gave, these are the 2 columns, 2 and 3 are the 2 columns, so 25 kilonewton meters. The sway mechanism, 42. The combined mechanism, that's 1 and 4, gave 56.86. And finally, combined mechanism 6, which is combining 5 and 3. So it's basically it's 1 plus 3 plus 4. Okay, that gave 58.7 kilonewton meters. And the critical mechanism, the solution, is this one here. Okay, it's the highest value of MP. It's the largest value of MP. And what you can conclude from this exercise is you never know what mechanism will give you the critical solution. You never know in advance. There is no way you can tell in advance what will be the most critical mechanism. And unless you consider all the possible combinations, you can miss the actual, solution. So therefore, it's very important to consider, as well as the independent mechanisms, you consider the combined mechanisms as well. Now, so the solution is 58.7 kilonewton meters, but the question is this the true solution? In order for this to be the true solution, it needs to satisfy all 3 conditions, equilibrium, mechanism, and yield. If I take you one step back, okay, so for this mechanism, which is the solution, okay, we have got 2 hinges, which is what we need for total collapse. Equilibrium is satisfied because we said that the external work is equal to the internal work. So the equilibrium is satisfied, the mechanism condition is satisfied, and therefore the only condition that we need to satisfy is the yield condition. Okay, so we need to satisfy the yield condition. Now, again, how do we satisfy the yield condition? How do we check it? We know the moments at D and F. Okay, so we have A, B, C, D, E, F, G. Okay, so we know the moments at D and F. We know the moment at A is 0 because it's pinned here. So we have a simple support. So this is 0. And the moment at G is 0. So the only moments that we don't know are the moments at B, C, and this one here, E. okay, at A, right? So therefore, what we need to do, we need to determine what the moments are at B, C, and E, and then compare them with the moment MP of 58.7, okay? If the moments are less than MP, that means the yield condition is satisfied. Otherwise, the yield condition is not satisfied, and therefore this is not a true solution. Okay, so let's look at that. So what we need, basically, we need to if I take you back here, we need to determine the moment at this point here, and at this point there. And there are different ways you can do that. You can take cuts. For example, you can start by taking a cut at there, and there, and then looking at the overall equilibrium. There are different ways and different sequences. You know, how you want, which one you start with first. It doesn't matter as long as you get the correct solutions. So the way I've done it is this. This is the frame. This is the mechanism, sorry. This is the mechanism. We know the moments at D and F, you know, are MP, okay? And always make sure that you show the correct direction of the moments from, you know, as from the mechanism, okay? So we have got moments at F and D. If you are not sure, you go back to your mechanism here, okay? And you can see the direction of the moments, okay? So we have this one here is anti-clockwise. This is clockwise. This is anti-clockwise, and this is clockwise. And this is how you show the moments on the free body diagram here of the moments and forces. Okay, so we have got the moments at D and F known. We know the moments at D and F equal to MP. And what we need to determine the moments at B. We need to determine the moment at C, and we need to determine the moment at A. We have got reactions. At A, we have a vertical reaction and the horizontal reaction. And at G, we have a vertical reaction and a horizontal reaction. And the dimensions are shown here, and the loading is also shown. So starting with, we could start, as I said, there are different ways in which, you know, there are different ways you can use to determine the moments MP, NC, and ME. One way I've done it is I've started by considering the equilibrium of the frame as a whole. So if you consider the equilibrium of the frame as a whole, we have HA plus HG. This is the horizontal equilibrium. We have HA plus HG is equal to 21 plus 21, 42. Then we have got the vertical equilibrium, VA plus VG is equal to 34. So this is the vertical and the horizontal equilibrium of the frame, okay? So this is the first step. So now we have got a relationship between horizontal and vertical reactions. The next thing, I mean, from here, again, you can try any of the cuts as long as it gives you the answer. What I have done in my case, I've considered the equilibrium of FG here, of this part. So if you take the equilibrium of FG and then take moments about F. So we take moments about F, okay? We have, so we're looking at FG only, okay? So we have, if we take moments about F, we have HG times 3, that's clockwise. We have HG times 3 equals anti-clockwise, we have MP. Okay, we have MP, and MP is 58.7, remember. Okay, so we have HG times 3 equals to 58.7, which is MP. So therefore, HG will be 58.7 divided by 3, which is 19.57. So the reaction at G the horizontal reaction at G is 19.57 kilonewtons. Is that clear? Okay, everyone, thank you. Then the next thing we can do, actually, we could go from here to, for example, D, or you can, or what I've done here, yes, that's exactly what I did. So if I take this subframe here, D, E, F, G, this one here, and so we take a cut at D, and we take equilibrium of forces, of all these forces about D. So we have Hg times the distance to D, which is 6, plus we have NP, okay, the Hg times 6 is clockwise. Then we have this NP here, which is clockwise, okay? So plus NP equals what we have anti-clockwise about D, we have anti-clockwise 21 times the distance to D, which is the perpendicular distance to D, which is 3. So we have 21 plus 3, okay? And also, don't forget the vertical reaction. This is also anti-clockwise about D, anti-clockwise. So we have Vg times the perpendicular distance to D, which is 4 meters. Okay, 4. So we have Vg times 4. Okay, so I repeat, we have Hg times 6 plus MP. These are the clockwise moments, equals anti-clockwise moments. We have 21 times 3 plus Vg times 4 about D. Okay, so substituting MP here by 58.7 and substituting Hg by 19.57 from the previous equation, that gives a Vg of 28.8 kilonewtons. Please do check it. So that gives you the vertical reaction at G of 28.28 kilonewtons. Okay. Is it clear, please, this equilibrium? Is it clear?
Yes, sir.
Yes.
Okay, thank you. So now we've got the everything. We've got everything for this side of the column of the frame. So we've got Fg and Vg. I can move on to the other side. Okay. Or actually, what I can do, because I know that Va plus Vg is 34, so I can take, I can substitute the Vg here into equation 2. That gives me a Va of 5.72. And similarly, I can substitute Hg into this equation 1 by 1957. That gives me Ha of 22.4. Okay, so this is substituting Hg and Vg into 1 and 2. Gives us it gives us the horizontal and vertical reactions at A. Okay, so we've got that covered. I think from now it's very simple, because once you've got the reactions at A, you can determine the moment at B by considering the equilibrium of AB, and then you can do the same by considering the equilibrium here to get the moment at C, okay, which is what I've done. So for EFG, what I've done here, I've taken, okay, I've done it the other way. That's why I said earlier about, yes, I've done E first. I've determined the moment at E first. So by taking the equilibrium of this member here, EFG, okay, because we know the reactions. So if I take a cut at E, we have Hg times 6, that's clockwise, Hg times 6 clockwise, equals anti-clockwise. Anti-clockwise, we have Me, that's anti-clockwise, Me. And we also have the 21 here, is anti-clockwise about E, 21 times 3. So plus 21 times 3. I repeat, clockwise, Hg times 6 equals anti-clockwise, Me, and 21 times 3. So that gives a moment at E of 54.42 kilonewtons, kilonewton meter, and this is less than MP. Okay, remember MP is 58.7. So this is less than MP, so that's good. Now we move on to the other side of the column, as I said earlier, to determine MB and MC. So first of all, considering this column here, ABC, so we are taking a cut at C now. We take a cut at C. So clockwise, we have HA times 3 clockwise, and then clockwise we have MC. This MC here is clockwise, okay? So plus MC equals anti-clockwise. Anti-clockwise, we have 21 times 1.5. 21 times 1.5. I repeat, about C, clockwise, HA times 3 plus MC equals anti-clockwise about C, we have 21 times 1.5. And then when you substitute HA by the value here, 22.4, and you can determine MC from the equation here, by, which will be 21 times 1.5 minus 3 times 22.4, giving 35.7 kilonewton meters. And this is the moment at joint C. And you can see that this is less than the plastic moment MP of 58.7. Is that clear, please? Okay, if anything is not clear, please just stop me, okay? Finally, we can take a cut at B. So we take a cut at B here. So we consider this part of the column AB. So we take a cut at B. Clockwise, we have HA times 1.5 equals anti-clockwise, we have MB anti-clockwise, and then we substitute HA by 22.4. So 22.4 times 1.5 is 33.6 kilonewton meters. Again, this is less than MP, 58.7. Okay. So now we've got all the moments known everywhere here at all the joints, at all the points where the loading is applied, everywhere we know what the moments are, and everywhere the moments are less than or equal to MP, okay? So we have got MP at D and F, we have less than MP at B, less than MP at C, less than MP at E, and therefore we can say with confidence that this mechanism is the true solution, okay? So this mechanism is the actual true mechanism, and the solution obtained, 58.7 for MP, is the true solution. Okay, so we can say with confidence that it is the true solution because all three mechanisms, conditions are satisfied: equilibrium, mechanism, and yield. Right? Any questions whatsoever, please, on this slide or anything, please? Any questions at all, please?
Yes, sir.
Yeah.
Can you tell us again why we don't need to consider the combined mechanism for the beam AC? For the beam AC, yeah.
Because it will give you an extra hinge at C. So you will have 3 hinges, more than that you need.
Ah, okay.
So
okay.
even if you try it, you will not. It will not give you the. It will not be a valid solution. You see what I mean?
Okay. Because we don't satisfy the mechanism. Yeah.
Exactly. Okay. Yeah. So in the future, when you consider mechanisms, if there is a combination that will give you more hinges than cancelling, then don't even bother.
Okay. Thank you.
Don't bother. You should only consider combinations that actually will eliminate the hinges rather than adding hinges.
Mm-hmm. Okay.
Okay, that's the rule. So not to waste your time, considering mechanism that will not be, part of the solution anyway. Okay, so that's the reason. Any other questions, please? Any other questions, please? Okay, so now we are going to use this here because we know the moments everywhere. We should be now in a position to actually show the bending moment diagram for this beam, okay? For this frame, sorry, okay? So this is the free body diagram, okay? We have got the moments determined just now, okay? And we've got the moments at D and E, which are equal to MP. And we have got the moments at B, C, and E that we have just determined from equilibrium. Okay. So now we, before you draw the bending moment diagram, remember to consider what the tension will be. Okay. So starting at column ABC, what can we say about the tension? The tension here at B will be on this side. Do you agree?
Yes, sir.
Yeah. And then we have tension at B on this side here. Okay. On the inner inside. Okay. Then we have tension on this side here at C. Okay. To the left. Then we have tension at the top. At C here we have tension at the top.
Excuse me, sir.
Yes.
I think the movement at C is in another direction because it comes minus.
Let me check. Where do you see where minus? It's positive.
MC value, I think it must be minus.
No, it's positive.
When you do 21 into 1.5 minus HA into 3, it gives minus 35.7.
And HA is 22, so 21. Okay, 21. Yeah, because it's bigger, isn't it? Because you've got 21 point. What is I think it's positive.
It's 22.4 into 3. It's bigger than 21 into 1.5.
What
so
is
it
H?
needs
What
to
is
be
that?
minus.
Oh, HA is 22, sorry, isn't it? 22, sorry.
Yeah.
I was looking at the wrong value. So it's, yeah, so it must be, so when you transfer it to the other side, it will be negative, yes. Let me correct it while we are at it. Okay, well spotted. So where is it? It's here, isn't it? Okay, so I've lost it. So we have minus, yeah, so we have minus 35.7. So that should be, because of such, that would be the other way around. Okay, these two here. And so that should be, I think that should be going down like here, like this, isn't it? And this should be going there, like this, isn't it?
Oh, yes, sir.
Okay, I will correct the directions here later on, okay, in the updated version. Okay, so as I said, so again, so we have tension at the top, tension at the bottom at D, and tension at the top there, tension on this side, etc. Okay, it's very important that you do this because otherwise your bending moment diagram will not look right. Okay, so it's very important that you get the that you get the tension on the right side, by looking at the direction of the moment for each case. Okay. So we have got this is the bending moment diagram, the fully annotated bending moment diagram for this frame, for this particular mechanism, the combined mechanism that we have considered. Okay. And that concludes this particular problem. Any questions whatsoever, please? Any questions? Any questions? Okay, is that clear, this problem?
Yes, sir.
Okay, thank you very much. Now, that's finished. So I'm going to take a break to prepare the next question. So I'm going to give you 5 minutes. Is that okay? So I'm going to mute myself for 5 minutes to prepare something. Remember, we're doing a revision here. So if you have got any questions, please prepare them. Okay, so I'm just going to give you a 5 minutes break and then continue. Okay, thank you. And as I said, prepare if you have got any questions for the revision, please. Okay, hello, welcome back. Okay, what I would like to do now is, have you got any questions first of all?
So can you show us the bending moment diagram?
For the one that we have just done?
Yeah, and go through it.
Okay, let me bring it back. Because I've closed it, so I'm sorry. Okay. Yes. Do you want me to go through it again?
Yes, please.
Okay. So what we said is we've got the values, okay, from the equilibrium here, okay, and these values we know them. These are the MP values at D and F, okay. I think I've corrected the direction of the moments at C, okay. So this is the moments at B, C, E with the correct directions, okay. Before you plot the bending moment diagram, what I said is you need to determine where the tension is, okay. For example, if you look at B here, you can see that the tension is on this side. Do you agree with that?
Yeah.
Okay. So again, here you've got tension on this side, on the inner side, and then you've got tension there, tension at the bottom here, for C, and then we have tension at the bottom at D and tension there as well. For E, we have tension at the top. So you can see here the moment is at the top. Then we have tension on the outside. So the moment will be outside here. And then you have tension there. So you've got the moment on the outside, okay, etc. And then, so we have got, at A, we have zero moment because it's, you can see it's simply supported, it's a pin. So we have zero moment. Then at B, we have 33.6, okay. So we have 33.6 there, okay. And then we have 35.7, that's MC there. So we've got 30.7, and you join the points together like this, okay, linear. Then we have, at the bottom here, we have 35.7, which is there. And we have 58.7, which is here at the bottom, okay. And at the top, we have 54.2, and then you join these points together because we have a point load in the middle. So the bending moment diagram will be like that. Okay. Finally, on this side, for this column, we have a moment of 54.42 on the outside because the tension is there. Tension is here. So we have 54. And then we have got tension on the outside. So we have 58.7. Okay. And finally, at G, we have zero moment, and you join the points together. And that's the bending moment diagram for the column, this column. And therefore, this is the bending moment diagram for the frame. Is it clear, or is there any aspects not clear?
No, it's clear. So
it's clear. Thank you very much. Any other questions on this problem or any other problem, please? Have you got any other questions, please? Okay. There is one tutorial question that I've given you. I don't know how many people have actually attempted it, and that's the. So I would like to spend maybe some time on the slab that I've given you last time. Okay. Right. This is the example of the triangular slab, but this time with the sides here fixed. So we have AB and AC fixed in this case. Okay. So it's the same problem we did last week. Okay. But this time the two sides are fixed. How many people have done it? Has anyone has attempted it at all, or done it, or completed it? Okay, it's not a very easy problem because of the geometry. It's not very easy, okay? But if you have tried to do it, well done, okay? But I don't know how many people have actually tried. Anyway, so that's the slab. AB is AC, AC is 8 meters, AB is 6 meters, and the angle here is 70 degrees. And we have M and M. By the way, this is my own problem. You will not find it in books or anything. I've create my own problems. So if you spot anything, let me know, okay? So first of all, we start by, this is the yield line mechanism here. Okay, please focus on this figure here, right? I'm going to make it a little bit bigger. Because I want to explain this to you, please. So we have the, So we have the yield line. This is the positive yield line, this one here. That's the positive yield line due to the sagging moment, okay? Because the edges here are fixed, AB and AC are fixed, we also have negative yield lines that I've shown here in dotted lines. Let me make them a little bit, I don't know if you can see them or not. Okay, so these are the negative yield lines. Okay, for from the negative moments. Okay, because when you have when we have edges, when you have sides that are fixed, what happened there? You get a hugging moment at this side here. So therefore, you have negative yield lines. And these are the yield lines where the slab could also fail, okay? So we have a positive yield line AD, then we have the negative yield lines along the sides of the slab where it is fixed. Is that clear or not, everyone, please? Is it clear? Okay, do you understand negative and positive yield lines, okay? Okay, so the rest is the same as last week. We have got the moments. These are the rotation vectors. This here in blue. Okay. Then you have got the moments. These are the moment vectors for the supported for the fixed sides here, okay? Right, using the right hand, yes.
So that red line is fixed for our hogging moment, isn't it?
Yes.
And is rotation same for hogging moment like that of sagging moment?
Yes, because the moment is hogging here, remember? So if you use the right hand side, if you use your right hand, okay, for the moment, but the right direction of the moment, because it's hogging, remember it's not sagging, then your thumb will give you that direction.
No, I have no problem with the hogging direction. What I mean is the direction of rotation for hogging is different than that of sagging, isn't it? Rotation, theta.
No, the theta is the same. Oh. The slab, this part of the slab, rotates out of, into the screen, okay? This part rotates into the screen. So if you use your left hand, your thumb will give you this direction, okay? Will give you this direction here as shown, all right? And the same here, this part will rotate into the screen, okay? If you use your left-hand side, your thumb will give you this direction as well. Okay, these are the correct directions. for the rotation. Okay. What I have shown, what I haven't shown here, sorry, I missed them, is actually the direction of the moments here, rotations. Okay, so I'm not sure. Let me check the direction. So what we have is, yeah, that's the direction. Okay, and then you have got it the other side as well here. Do you agree with that, everyone, please? Agreed?
Yes, sir.
Okay, so now what we do, we need to determine now the internal work and the external work for each of the, we need to start, if we start with the internal work, what I've done it in one table. The top half is for the internal work for the sagging, which is this, okay? And then the bottom here is for the hogging moments, okay? I want you to follow this with me, please, very carefully, and stop me if you've got any question, okay? Starting now, concentrate on the sagging here. Concentrate on that, okay? So region A, this is region A, okay? This is A. ABD is region A, okay? ABD, and ADC, sorry, is region B, okay? So we're starting with region A here. This is the vector moment, okay? So MX, okay? In the X direction, it will be negative, and it's minus M, okay? And we're looking at this vector here, okay? So projected on the X-axis, we have minus M. Projected on the Y-axis, we also have minus M because it's going down. The length of the yield line, this is the yield line, AD. And if you project it on the X-axis, it's AE. Okay, it's AE. If you project it on the Y-axis, it's DE. Okay, the rotation, okay, the rotation is, okay, we're looking at this region here, remember? So the rotation is 1, okay, over HD, the perpendicular distance here. 1 is the displacement there, divided by HD, and it's cos 70, okay, because you're looking at this vector here. Let me make it a bit bigger. Okay, we're looking at this vector here in blue. This vector here. So you can see that the rotation vector, I can't even click on it because it's blocked together. So this, can you see here? This vector here in blue, that's the rotation vector. The horizontal component is cos 70, because that's 70 degrees, okay, cos 70, and it's opposite to the X direction, so it's minus. So it's minus, okay. So, sorry. So we have got, minus 1 over HD times cos 70, which is the horizontal component of this vector here, okay? And when you project it on the vertical axis, again, it's down. When you project this here on the vertical axis, it's minus 1 over HD, this time sine 70, okay? Then for the work, I couldn't put it all in the same, in the box here. It's very long, so it's the next page. So what you do, you take mx times lx times theta x plus my times ly times theta y. Then you repeat the same for region B, which is this one here. Region B, we have, this is the vector. So on the X direction, it's positive. On the Y direction, it's also positive when you project this on the Y axis, positive. The yield line is the same. So when you project on the x-axis, it's AE, and when you project on the y-axis, it's LY. Now for this is the rotation vector here in blue. This one in blue. So the displacement here is 1. Okay. So therefore, the rotation, this rotation here is 1 over dE. 1 over dE. And on the y-axis, it's 0 because this vector is horizontal. So when you project it on the y-axis, it's 0. All right. And then the work will be mx times Lx times theta x because theta y is 0. So it's only the x direction coming into play. Is the internal work for sagging clear, please? Before I move on to the next one for the hogging. Is it clear, please? Any questions?
It's clear.
Okay. Anyone else? Any questions? Okay. Please unmute yourself and ask if you have any questions whatsoever, please. Now let's look at the hogging. Now we're looking at this here. Okay. This there. All right. So region A, we're starting here, and we are looking at this edge, this side here. Okay. So this is the vector. Projected on the x-axis is minus, you can see it's -1 and minus m, sorry. Projected on the y-axis, it's also, it's down, so it's minus m. Then we have, this is the yield line, AB. Can you see that? In dotted line. Yeah, that's the yield line. So this yield line, now we need to project it onto the x-axis. This is 6 meters. AB is 6. This is 6. So when you project it on the x-axis, it's 6 sine cos 70. 6 times 6 cos 70. And on the y-axis, it's 6 sine 70. 6 sine 70. Okay. The rotation is the same because it's the same vector here. We have the same because the axis of rotation of this part is about this axis anyway. So that's exactly the same. Okay, that doesn't change. Now going to B, we are looking at this here. On the x-axis, we have M. On the y-axis, we have 0 because it's a horizontal line. It's a horizontal vector. So on the y-axis is 0. Now the yield line, can you see the yield line? AC here, dotted line. This dotted line. On the x-axis, it's 8 meters. Okay, that's given. On the y-axis, it's 0. And the moment, obviously, is the same as before. The rotation, sorry, are the same as before. Is it clear, please, for hogging, please? Is it clear? Everyone, okay? So silence means you have no questions. Is that okay?
It's
so
clear,
now,
sir.
Yeah, thank you. So next, what we're going to do, we are going to, as I said here, we are going to go and multiply this, mx, lx, theta x plus my, ly, theta y for each of these regions and add up everything together. Okay, so this is my next step. All right. Now, before I do that, what I've done here, it's a bit tricky, but no, it's not difficult. It's just geometry. It's not difficult at all. It's just the geometry because I need it, okay? I need it. You see, if you go back here, okay? If you go back here, if you see what we did last week, actually, look, before I don't want to jump stages, so let's go here, and then I explain what I'm doing. Okay. So internal work. So the internal work is mx lx theta x plus my ly theta y, and we do it for each region, for region A and region B. Okay. Now, so you take the table and you multiply everything together, okay? That's what I'm doing, okay? So when you do it, this is what we get, okay? This is for, okay? And remember, you've got the sagging and the hogging to do, okay? This is the this part here up to here, that's the sagging, okay? And this part here is for the hogging part, right? And then you add them up together from the table. Is that clear? Now, then, what I did here, sorry, this is from the table. So up to there is sagging, and this is hogging. Okay. Then what we did is we use the fact that cos theta is AE over AD, and sine theta. So we're looking here. Cos theta is AE over the hypotenuse AD, and sine theta is the opposite, which is DE over AD. Okay, so which is what I've done here. So, and then I substitute that into the equation here. So AE will be AD cos theta, and DE, this one here, DE is AD sine theta, and this substitute, okay? And you do it everywhere. And then when you get to this part here, we've got cos theta and cos theta. So that's cos square theta, okay? Because you can see it from the table. Let me take you to the table here. When you multiply, sorry, it keeps going back. So when you multiply Lx and theta x, you can see that you got cos theta and cos theta. So that's cos square theta. And when you multiply Ly and theta y, you got sine square of 70, okay? Which is what we have here, okay? So you substitute, which gives you this equation here after simplifying, okay? Then we use cos theta plus 20 is HD over AD, which is this one here, this angle. And we did explain it last week, why this is theta plus 20. So cos of this angle is the adjacent HD over the hypotenuse, which is AD. So cos theta plus 20 is HD over AD. All you need is do it slowly, okay? Don't rush it. Do it very slowly, and you will not be mistaken, okay? So then I substituted again into this one, into the equation here, which gave me this equation for the intended work. The only problem I have here is that I don't know AD, okay? And I can't express it in simple terms like this here. That's the problem, okay? Because if you substitute AD here by cos theta times, by AE over cos theta, it doesn't help you because you still have AE. So we have got AD here to find, okay? And I need to express AD as a function of theta somehow. I need to express it as a function of theta somehow. And let me take you, this is AD. This is AD. So really what I need to do, I need to find a relationship, the relationship between this AD here and theta. Because if your yield line changes, if this yield line here moves, the angle here will change with the yield line. You agree with me, okay? So there is a relationship. Therefore, there is a relationship between AD and theta that we need to find. All right. And the way I've done it is I've taken the slab, the triangle, and I've used parallel. I've used the first of all the angles here to get AK, and then to get BK from the angle from the 70 degrees angle. Okay, then what I did was I use similar triangles, this two here, this one, and this one. Anyway, you follow this. So we have got AK is AB cos 70, and then we have BK is AB, this one here, sine 70, and we know AB is 6. So we know AB is 6. So therefore, I can determine AK is 6 cos 70, BK is 6 sine 70. So BK over AK will give me here, okay, BK, can you see that? BK over AK is equal to DE over AE, okay, using similar triangles, okay. I don't want to waste too much time here. Please go through it on your own. It's all, you know, from simple geometry here. It gives you, at the end, it gives you an angle of, it gives you a relationship between AD and theta as this, okay? Because effectively what I've done here, I've determined the angle alpha here. That's what I've done, okay? We know theta is, we know this is 70. We know this is 6 meters. This is 8 meters. So I've got an angle for alpha. I've got the value for alpha. And then I substitute it into the equations here, into the equation here, which gives me a relationship between A, D, and theta. Then what I've done, I've taken that relationship between AD and theta and back substituted into the equation here, okay? And then that gives me the internal work as a function of theta only, and m, obviously, and m. So the only variable will be, in the internal work equation, will be the angle theta only, okay? The external work, no change from what we did last week. That's exactly the same for the external work. So you did the external work for for region A and B. It gives you 7.51 W as we did last week, okay? Right, so then the next step is, what I did was, so I've equated the external work to the internal work, okay? So I've equated the external work to the internal work, and, and so what we have this here, this long expression of the external work equals to the internal work 7.51. And you can simplify this part here. You can simplify it. That's identical to the expression that we had last week, if you remember. Okay, so go back to that, and you can simplify it to this. Okay, you can simplify it to this, plus this part. This is the new part due to the existence of the sagging moments. Okay, that's the new part here, which is there. Okay, so this is the expression now. We have the external work equals to the internal work here. I've called this function here f theta, this here, from there to there. Okay, without the m. So that's m times f theta equals 7.51 W, and f theta, as I said, is this expression here. Right, and AD, we have just determined AD, it's equal to this, okay? So then what I did, I created the table, and I've started using values of theta, 5, 10, 20, etc., up to 40, okay? For each value of theta, I've calculated AD. Then I substituted AD into the equation of f theta, which gives me f theta, okay? And then what you can see that the optimum value is actually at 35, because the values here started to, you start with a large value of f theta. I didn't calculate all the intermediate values, but basically it will start decreasing until you get to 30, you get 7.33, then at 34, you get 7.2, then at 35, you get 7.202, so it drops again, but then it starts increasing again. So it starts increasing again, okay? And therefore, the conclusion is that this is the optimum value, okay? This is the optimum value between 34 and 36, right? So therefore, the optimum value is for theta equals 35 degrees, giving a value of f theta of 7.202, which you can substitute here, okay? So that gives you an m over w, which will be 7.51 divided by 7.202, giving 1.04. W m over w 1.04. What do you know? What can you conclude from this? If you compare this with what we did last week, what's the observation? What was the angle? What was the optimum angle last week? Do you remember the solution last week? What was the optimum angle?
35 degree.
Exactly, 35 degree. So it's not. Does it surprise you? Is it surprising or not? It shouldn't surprise us. Why? Because look, you have the same degree of fixity. Okay, you have the same degree of fixity there, and therefore, all we have done between having this and here, simply supported or fixed, is we have changed the degree of fixity, but on equal rights. Okay, so in other words, we had them simply supported. By having them fixed there, that angle will remain exactly the same. The optimum angle will be the same. What will be different is this here. That has changed. I can't remember the value last week, but we had something
3.63.
Exactly, something like that. Okay, so the value of m over w, because we have got now we have the moments at the supports on the two sides. So obviously the optimum m over w will change, but not surprisingly, the optimum the angle itself did not change. Okay, and this concludes this problem here. As I said earlier, the geometry is a little bit I wouldn't describe it as complicated. I would describe it as lengthy. It's a bit long to actually to actually work out the relationships, but it's all linear geometry. There is nothing complicated here. It's all to do with tan, trigonometry and similar triangles. There's nothing really difficult there. Okay, so I will leave it to you to actually please go on this problem on your own time. Okay, and if you spot anything, or if you have got any questions, or if there is anything not clear, please get back to me, email me or scan it or whatever, and get back to me with any questions. Okay, so
Sir,
yes.
Previously, when you didn't do much simplification, we got the value as 32.5 degrees. So does that matter? Later
Which
when
one?
you simplified with trigonometry, the same problem, this problem, similar one.
Did we have 32.5?
Yeah, you got 32.5 without much simplification. But when you started simplification, the later value was 35 degree.
Oh, I don't remember. I remember the final answer was like 35, isn't it?
Yeah, the final answer was 35 when you simplified with trigonometry. But before simplification, when you directly use the angle, the value was 32.5 degree.
I have to go back to that and check it.
Okay.
I don't remember. Yeah, but it's but the method is that's the method to use it anyway. Okay, I will check. I will check the previous answer. Okay.
Yeah. And m by w value as well, before you got 3.18 and after simplification you got again 3.63. So the value is quite different. So will that matter? 3.63 after simplification. with trigonometry, but when you didn't simplify it, you just got 3.18.
Instead of 3.6, did you say?
Yeah, 3.18 was without simplification, and when you simplified with trigonometry and you got the solution, it was 3.63. So there are two different type of values.
I don't know. I'll have to go back to that problem and check. Okay.
Okay,
I think
so
what
I will mail you that.
Yeah. Email me, or I will check it myself. I will check the lecture myself. Okay. As I said, these are my own problems. So
Yeah.
it's if you spot anything, let me know. Okay.
Okay.
Any questions, please? Anything at all? Okay. I think this problem is good because it shows you how to when you have got the sagging negative and positive yield lines together, how to handle the problem and how to get the optimal value. Okay, it's very, very important that you understand the steps involved here. Okay, as I said, the geometry usually is not that difficult in terms of solving because it's all linear sort of algebra. You need to know your trigonometry for the exam. Remember, this is an open book exam because you're doing it online. Okay. What my advice to you is this: I will just spend the last few minutes to give you some tips for the exam. For the exam, get the identify which websites you need for trigonometry equations relations. So you don't waste the time on the day, just in case if you get a question where you need trigonometric equations, you don't waste the time, on the internet looking where do I find the information? Okay, so that's something you need to do is find out where you can, a trusted website where you can get the, any mathematical support that you need. Okay. Right. I mean, to be honest with you, I think a lot of the geometry here is really GCSE level. So you should really know all that, cosine, sine, tan, all that parallel, parallel axis theorem to, when you calculate second moment of area, all that stuff is really, you should know it. But what I'm saying is that if you do need any maths to support you on the day of the exam, if I were you, I would identify some good website where you find all the all the equations that you need to help you with the exam. That's what I'm saying. Okay, but you shouldn't really need that. You should really be able to use your past knowledge of mathematics to solve the problems. Okay. For the again, for the exam, this is what you need to know, and please listen to me carefully. You need to know how to determine the centroid of a shape. That's number one. You need to know how to determine the centroid of shape. You need to know how to determine the second moment of area of a shape. Okay, and then you need to know how to determine the Z and the S, the plastic and the elastic and the plastic section for the shape. Okay, the elastic section modulus and the plastic. So you need to know these things. Okay. The other thing you need to know is obviously you need to know the rules, how to determine the mechanisms, and then you need to know how to solve the different mechanisms. You need to understand the theorems, equilibrium, mechanism, and yield, so you can use them appropriately. And then the rest really is what you did in the past, like you need to know how to obtain the moment at a particular cut. If you take a cut, how you determine the moment there. The other thing you may need to know is differentiating. So if you need to differentiate about a particular unknown, for example, in the optimization, if you have an optimization problem where you need to differentiate and equate to 0, so you need to know how to carry out a differentiation to obtain an optimum solution. So these are all the things that you need to know for the exam, no more. Okay, so go through the example that we did in class, go through the lecture notes, and you will be absolutely fine for the exam. Okay, and I'm talking about my part of the exam. David will tell you a little bit more about his part of the exam, but for my part, really, that's all you need to know. Okay, you will have one equation where you will be asked to determine the plastic and the elastic and the shape factor. Okay, and then you will have one question where you will be given a slab to analyze using headline, and then there will be an example of plastic theory, which could be a beam or a frame, okay, that you need again to solve using plastic theory of structures. Have you got any questions about that?
Excuse me, sir.
Sir, will there be theory? Oh, sorry.
Yes. What do you mean for your part of exam?
Oh, sorry. No. I'm talking about here. Sorry, we got the MSc student. They have got to. I think now both of you, because you have got only exams. You have only my part, isn't it?
Okay.
Because you got the coursework. No, that's fine. Ignore what I said. Yeah.
Okay.
So the exam will be 4 hours. 4 hours, and there will be a question on, as I said, on. You'll be given a section, cross section, okay, where you need to find the S, S, Z, MP shape factor. There will be a question on the, slab, headline analysis, and the question on plastic theory, frame or beam. Okay. Any other questions?
So
Yes.
will there be any theoretical questions?
If there will be what, sorry?
Theoretical questions.
No,
right?
No.
Yeah.
It's all calculations. There will be no theoretical questions, no. Any other questions?
Sir, in practical field, after getting the year line, what do we actually do after that?
What do you mean after what?
After we know the direction of the yard line, the particular yard line in a slab, is it used for strengthening of the slab later? Like what I mean is, what is the use of this yard line actually? What do we do in the design with this?
I did explain it before. Here, the head line gives you a relationship between the moment and the load. Okay.
Yeah.
Now, if you use Eurocode 2, for example, or whatever standard you're using, the code will give you the moment. Okay. If you know the reinforcement of the bar, how the bar is reinforced, etc., and all the details, the code of standard, whether you're using Eurocode or American or whatever, you can get the moment of resistance from the code, and then using this here, this will tell you what is the load, at what load the slab will fail.
Yeah.
And that's the relationship between the theory and the design.
Yeah.
Okay. So the theory will give you the relationship of moment and failure load, and the code, the design will give you the moment, and therefore when you combine the two, you can obtain the load at which the slab will fail. Okay. Any other questions?
And sir.
Yes.
It will be, you say at the exam it will be three or four questions regarding slab, plastic theory of beam and frame, shape factor.
Yes.
And what other?
That's it. So you have one shape, you will have a shape of cross section of that you will need to determine the S, Z, MP, etc. Okay, and then you have a slab, and then you have a frame or a beam for the plastic theory. 3 questions.
Okay, thank you, sir.
You're welcome. You're welcome. Any questions, please?
Excuse me, sir. If you have time, could you upload another example about the how to determine the shape factor? Because I think we have just just one example.
Okay, no problem. I mean, on your timetable, today is the last lecture. But however, do you want me to have next week one revision session at 12 o'clock, 1 hour?
Yeah.
And then we can go through shape factors slowly.
Yes, sir.
Okay, no problem. I will upload some more questions, and next week we'll have 1 hour revision, please, to everyone. So next Monday, 12 o'clock, 12 to 1, I will go through the a section, because I think we have done enough for slabs and frames. So what I will do, I will go through a typical example where I show you how to determine the centroid, the second moment of area, how to determine the Z, the S, the MP, the shape factor. Okay?
Thank you.
No problem. You're welcome. Okay. In the meantime, if you have any questions, please keep emailing me. I always respond to the emails, and I usually do it very promptly, except if I have got some meetings or something. Okay. But otherwise, please let me, send me any questions that you have. Okay. So if you haven't got any more questions, can I take a final question? Any other questions?
And shall we have class tomorrow from 1?
Yeah, that's kept. That's normal. Yeah, I'm talking about the Monday class.
Good. Okay.
Okay. Is that okay, everyone, please? Okay.
Thank you.
Thank you very much. Thank you. So I see the MSc students tomorrow, obviously, as usual. And for the rest, I see you all next week, Monday, 12 o'clock, for a final revision session. I don't know, what is your do you know the date for your exam?
It's 14th.
Yeah, you
14th
see,
April.
exactly. So it's not really, it's really very close. It's very close, really close. I mean, normally we should be stopping all classes this week to give you time to revise, but I'm more than happy to give you 1 extra hour next week, okay, as a revision. So come ready with any questions, okay? So all the best, and see you next time. Bye-bye.
Bye. Thank you.
Thank you, sir.
Okay, bye-bye. Bye, everyone. Bye-bye.
Thank you, sir.
Bye-bye.